So in this video we're going to be learning about capacitance. Now capacitors are very useful. You can use them in oscillator circuits. Pretty much what they do is it's two metal plates parallel with each other, or just two metal surfaces parallel to each other with a little gap between them. And when you run a voltage through them, they store a charge. They store voltage, and then they discharge depending on the highest voltage that they can consume, not consume, but store. And they're, like I said before, they're pretty cool. You can use them in oscillator circuits. They're very useful, even as alternating voltage sources sometimes. So let's get to the equation. We have capacitance is equal to the permeability of a vacuum, which is 8 times 854 times 10 to the negative 12 times the area over the distance that these two surfaces are separated by, multiplied by the dielectric constant. Now dielectric is pretty much any material that you put in between these guys, between the two plates, that allows them, it increases the capacitance, how much they can. It could be like a crystal, it could be some type of chemical or material. And capacitors, we measure those in farads, or denoted as F. Now, in electrical circuits, you're either going to see capacitors like this, which shows a what you call electrolytic capacitors, and they're polar. So they have a plus, they have a minus side, and they have this little curve. Or you're just going to see parallel plate capacitors, which are just two straight lines. And it's interesting about these guys, if we look at the timetable versus voltage, you'll see that during the beginning it's going to be charging up, and then when it gets to some voltage, it'll start to discharge over time. Now, in parallel, you can make an equivalent circuit out of these guys, which is kind of inverse from what you can do with a resistor. So when they're in parallel, you just add them up. You get C1 plus C2, you get CEQ. And in series, it's like having resistors in parallel. You do C1 times C2 over C1 plus C2 is going to be equal to your CEQ. Now, to find current, you have the current is equal to the capacitance times the change in voltage over the change in time. And if you take the antiderivative of this, we have V as a function of t equal to 1 over capacitance times the integral from t0 to t to t0 to t, and we have the current I d tau plus V of t0, t being your original time. So this is pretty cool. Sometimes in problems in college, they'll give you the current, and they'll give you the voltage at some time 0 and some time, they'll say find the voltage going from 0 to t, and say they give you a current too. Let's say from 0 to 5, and they give you capacitance. You just plug them into this integral here, and let's say V of 0 is just 0. So you just be taking this integral of whatever your value is here, and just solving the integral for it. So it's pretty simple.